So, what is game theory? Is it a theory about finding optimal game strategies? The mathematical analysis of competition? A process by which mathematicians take a simple game of tic-tac-toe, ruin the fun of it, and transform it into a huge tree structure? Well, those are all part of the answer. But what is game theory really? I would argue game theory is the mathematics of decision making. Whether you're thinking of your next chess move or choosing your answer to an opposing political candidate, you are taking a decision that will affect others' decisions and that will ultimately benefit or detriment all parties to varying degrees. Of course, it would be a mathematical crime to talk about game theory without embracing its roots in actual recreational games. In terms of history, initially, mathematicians like Girolamo Cardano and James Waldegrave studied games to win bets and discover better game strategies. You know, the good old days, when the player could actually be smarter than the house and ruin gamblers with more than just luck. Eventually, economists like Antoine-Augustin Cournois and John von Neumann extended these ideas to all forms of decisions, particularly economic decisions. Game theory officially starts with John von Neumann's 1944 book, Theory of Games and Economic Behavior, where the term game theory was coined and the axioms of game theory were determined, establishing it as its own field. It's a major shift in scale. When a game can be as big as an economy, players are not necessarily human. Monopolies, governments, corporations, and many other institutions can also be players. In this context, the idea of a payoff is quite literal. Corporations will most likely prioritize financial gain and minimize costs, leading to predictable actions. Nowadays, game theory is about competition, cooperation, diffusion, and stabilization of behaviors in biology, robotics, and much more. Hunting patterns, migration, and many more animal behaviors can be explained through game theory. These behaviors may also be simulated through intelligent agents, better known as bots, who constitute another large area of research for game theory, multi-agent systems. So Wolfram's game theory functionality can be divided in three major parts: matrix games, tree games, and game theory data. Let's start with matrix games, also known as simultaneous games. Game theory often seems meaningless without examples. So let's take me as an example. My wife and I would like to get a pet. However, I know she prefers dogs and she knows I prefer cats. For Christmas, each of us choose to wish for either a dog or a cat. These are simultaneous decisions. Now we can combine those decisions in a matrix game in the following way. Before I explain my choices, let's also visualize it as either a dataset or using the matrix game plot function. Okay, so we have a better view of things. Here, if we both choose dogs, I'll be happy to have a pet, and she'll be even happier because she has the pet she wanted. If we both choose cats, she'll be happy to have a pet, and I'll be the happier one because it's the pet I wanted. However, if we choose different pets, we'll have to get both pets. And we both hate the idea of having a dog and a cat simultaneously in the house. So what do you think we should do? Any guesses? We can use fine matrix game strategies to get us the Nash equilibria, which can be seen as a set of decisions where all players can't individually improve. Here we can see three different strategies. We could both choose to have a cat, we could both choose to have a dog, or we could both choose a cat or a dog depending on some probability, which equalizes our expected payoffs. We can use matrix game payoff to see the expected payoffs. As you can see, the equalized strategy is far worse for both players. so it makes sense for us to agree on the pet we'll put down in our list. But to me, that doesn't really solve the issue. It feels like we're back at square one, having to choose between dogs and cats. So as a game theorist, I'll change the game a bit. Tree games are also called sequential games, as players take actions sequentially. Again, we both have the choice between writing down dog or cat. However, when I combine choices in a tree game, I have to order them sequentially. Again, let's create a game combining those decisions, and let's visualize it. In this tree game, I choose first between a cat and a dog. I then show my wish list so that my choice is known. Then, it is up to my wife to choose between a dog or a cat. Find tree game strategies allows us to find the subgame perfect equilibrium, which can be seen as the Nash equilibrium of tree games. In this case, the strategy proposed is for me to choose cat, and for her to choose dog if I choose dog, and cat if I choose cat. This corresponds to the expected payoffs of 2-1 in my favor, using the tree game payoff function. Clearly, this formulation of the game advantages the first player to act. So you now have a basic grasp of game theory in 14.2. Thankfully, most of the remaining functionality is designed to take your understanding of game theory to the next level. Starting with game theory data, the function has 49 different well-known games that you will encounter when studying game theory. More than just a fixed game, game theory data gives you access to the classes, the description, and the source of each game. Many of these games can be extended to n players, such as this Dinner's Dilemma extended to 6 players. This functionality should enable you to dig deeper and learn while playing with the data. Game theory data also contains more exotic games, with properties going far beyond what I could explain in a single talk. This deep functionality is paired with fine-tuned documentation to enable learning and usability, where all the details of these new objects are explained simply enough for anyone to appreciate and use game theory. The examples follow simple workflows applicable to any game theory tasks. Understand the game, generate it, visualize it, and solve it. The game theory documentation has a lot of these workflows, with almost every game documented with examples and explanations. Of course, So what would it actually look like when you'll visit our documentation? Here's the guide page, and so you should have a better idea of exactly what to expect. So as mentioned, first we have matrix games, and second we have tree games. And so for each of those types of games, you have the object itself, which for matrix games implies that any simultaneous game can be expressed as a large matrix. And so you see that matrix structure over here. And for tree games, any game follows the tree structure. And so there's nesting in each of those actions possibly, which follows the same kind of nesting you would see in a tree. So coming back to the functions, each of those games have plotting functions, matrix game plot and tree game plot. Matrix game plot takes a matrix game as input and a strategy also. Same for tree game plot. It takes a tree game and a tree game with a strategy. Then we have a solving function, find matrix game strategies to find the Nash equilibria, and find tree game strategies to find the subgame perfect equilibria. So we have the matrix game and the specifications. It's worth mentioning that those functions have methods that could be find instance and solve values. You could see find matrix game strategies as an application of our state-of-the-art polynomial solving. Find tree game strategies is a bit different. This relies on backward induction. So this solver is a bit simpler. Then for each of those functions, we have verify matrix game strategy and verify tree game strategy to verify if any of those strategies are indeed a Nash equilibria. turns out that this computation is much simpler than the solver, so it's very useful to verify any of those. So it's very useful if you ever want to try to guess optimal strategies, make your own searching algorithm for the Nash equilibrium. Same for verify tree game strategy. Then we have matrix game payoff and tree game payoff. For matrix game payoff, we have different properties, such as, of course, the expectation, but also marginal distributions, multivariate distribution, simulation, variance. As for the tree game payoff, we have different types of adversaries. These allow you to assume some actions are done by either perfect or random players, and therefore it allows you to play games against players. We have two new options, game action labels and game player labels, if you want to label the actions or the players. And of course, our big game theory data, which covers all the predefined games.